Now I'll go to the Excel sheet and help you understand how to check this out. So we'll go step by step. First things first, let's start with the customer demand. The customer wants 12,000 pieces of 12,000 plus 6,400, 18,400 pieces. So 18,400 pieces, 20 days. This is the information that is given in the example, okay, case study. So if it is 20 days, D3 by D4, that is 18,400 divided by 20, which is 920 pieces per day, which is 460 pieces per shift. 460 pieces per shift, because one portion is clear. So this is the pieces required per day. We have said per shift how much is required, per day how much is required. It's clear. Now let us come to the time. 8 hours. 8 hours is how many seconds? 28800. So when you have some break timings in between. So 20 minutes break. How much is 20 minutes break? 20 into 60. Okay, so 7 hours 40 minutes. That is equivalent to 27,600 is the available time. So you have totally 28,800. You have 20 minutes break. There is some lunch time, tea time and all that. And you have, now things are very simple. Let's see. Now takt time calculation. What is takt time? All of you write. Available time will come in the numerator or customer demand will come in the numerator. They have a small doubt. See, the unit is seconds. If the unit is seconds, definitely time should come on the top. As simple as that. So have that logic. If the logic is clear, turnaround time is different. This is called takt time. In fact, in one of the modules, we'll talk about different times, okay? Even good times and bad times also. So there we will discuss turnaround time. What is that? Turnaround time is generally used in softwares, right? SLAs, like BPOs. And now here we use what is called a takt time calculation. So available time by customer demand. Customer demand is 460 per shift and available time is 27,600 per shift. So takt time means is the drum beat every 60 seconds that you will have to produce one component. Why only 60 seconds? It's very simple. It's a reverse logic calculation. Suppose if you have to give pani puri, have you eaten pani puri? Let me give this example. You are eating one puri in 1 minute, properly eating it. One puri in 1 minute. And after that, he has to serve you. Suppose you need 60, the available time is 1 hour. Okay, 10 minutes will take because you're not eating too much, okay? Available time is 10 minutes. You have only 10 minutes with you and you have to catch a bus. And you come to the Pani Puri shop. So available time 10 minutes is clear. And you need 10 Pani Puris. You said 1 plate of Pani Puri. And 1 plate of Pani Puri is 10 numbers. In what rate should he supply you the Pani Puri? Your demand is 10. The available time is 10. What rate should he feed you the Pani Puri? 1 minute. Similarly, you have 27,600 seconds and you need 460 pieces. So the question here is, takt time is the only time which is not measured using a clock. That's what I have observed. All the other times are actually measured. You can be measured using stopwatch. Takt time is the only thing that is not measured using stopwatch. It has to be calculated based on the customer demand. So the customer demand is 460 and I have 27,600 seconds available with me. So every 60 seconds, if I give a piece, 60 into 460 is how much? This is what is called as tag time. Okay. Now you need, how many pieces do you, so customer demand per day is how much? How much is the daily requirement of the customer? How much he requires per day? So customer needs 920 pieces per day. Now let us come here. In stamping, already it is 5 days of coil. Let's leave the stamping alone. Now in S welding, 4,600 pieces of left and 2,400 pieces of right, and totally 7,000 pieces. So what is the formula to calculate the 7.6? 11,000 pieces of this thing, 1,700. 1,700 divided by, that's why I have introduced this per day we want 920, per day we want 920 and all that. And then it is converted into, so totally, if you do this, it is 23.6 days. Okay, now cycle time, we know 1 second for stamping, 39 seconds for this, 46 seconds for this, 62 seconds for this, 80. So the most disheartening portion is we will actually, in value stream mapping, the process lead time, or earlier they used to call, manufacturing velocity. These days, after the transactional mapping started coming, they started calculating PC in the comment box, process cycle efficiency. And it is value added time by total time. And the total time is actually 23.6 days plus 188 seconds. So for all said and done. So now the point here is whether it is easy to think of logically. Suppose if you want to increase the throughput time, what should we do? This is a question. Suppose it will take at least 23.6 days before one order is delivered to the, if a new order comes in, it has to go through first in, first out of all the inventory and then come out. So it will take 23.6 days for any new order. If you put in the initial, it is like haircut only. Suppose, let's say that you are in the queue. You go for haircut first. Then after that, it's not done on you completely. Okay. After haircut, you'll have to go for shaving. After, it's like a medical test. You go to for medical checkup. First, you stand for blood test, then you stand for ECG, then you wait for this thing. Suppose if there are a group of patients, if you have to go through this entire queue, after these people are completed, then only you will be taken out. So in manufacturing, if you have this, if you want to actually improve the lead time, that is, improve the lead time means shorten the lead time. Instead of 23.6 days, if you want to deliver in 12 days, will you work on cycle time or will you work on non-value adding activities? Just a clarification, 23.6 days is based on the present inventory. Value stream mapping is a snapshot at that particular point in time. You might, as a team, say that this 7,000 is not a representative figure, and you can check the past records, change this 7,000 into 3,500, it is okay. In your snapshot, if you put, you're not going to take a decision based on that snapshot. That is why the subject matter experts are there. You need to collect some past data, and the team should agree, yeah, the 7,000 is a representation of the actual situation in the factory, means take 7,000. Suppose 7,000 is, no, there is some new order came and we got some excess material and we'll clear it off. Normally only 1,000 is there in that station, put 1,000. So these sporadic causes, these exceptions, you can remove it. Because why? Because, and you have to remove these exceptions and validate it with what is normally happening through data and not through somebody saying something. You need to back it up, and only then will be a true improvement. Non-value adding activity, suppose if I say generally even in TOC, if you see, heard Dr. Elio Goldrecht on this concept of inventory. This is called drum buffer rope effect. In drum buffer rope, when he is talking about improvement, throughput time increase, he gives U-shaped curve. So what I was saying here is, If you see the theory of control, theory of constraints, okay, theory of constraints, drum buffer rope effect, when he is explaining that concept, there is a U-shaped curve of inventory where he talks about management attention. Management attention. What catches management attention? So what he says is, when there is a management attention is there when the inventory is too low and there is a stock out, and management attention is very high when there is too high an inventory. I'll repeat, management attention. The management antenna will go up if when the inventory is too low and there is likely to be a stock out, then management, everybody will become very, very attentive. This is his logic, Dr. Goldr's logic. Okay? And the management attention is very high when the inventory is too high. So which means that there is an optimal inventory in between, and he characterized, Hitachi case, very nice. Exactly in Hitachi case, okay? So so Gupta ji has read the Hitachi case of drum buffer rope effect, okay? So it is a U-shaped curve. On the left side of there is a line on the top, that is the management attention is very high when the inventory is low. So if the x-axis is less inventory to more inventory, and the y-axis is less inventory to, this is the x-axis, x-axis is from left is less inventory and right is more inventory. On the y-axis, bottom is less management attention and top is more management attention. If you put a U-shaped curve like this, let me try to put it in annotation here. Okay, so that we can use this feature of annotation. Okay, so I'm putting a U-shaped curve here, and here it is a x-axis. So this is low inventory, and here this is high inventory. Okay, this is management attention is low here, and the management attention is high here. So Taguchi says that if the specification is at the center, so look at the center. Suppose if the diameter of something is 10 mm, you have to be exactly 10. If it is less than, also it is a loss to the society. If it is more, also it's a waste to the society. So he says, okay, the point that I'm trying to tell is, he says the best thing is to take the center and cut the inventory by half. That's why I put 24 days, put it into 12. You are safe. You are safe with cutting inventory into half. So it's always better. The present inventory, you are always safe. You will not do a mistake. That's what Goldred proves using theory. And then just look at the phenomenal effect on the lead times. But the point here is, the challenge is this: whenever you cut the inventory, the inefficiencies will surface out. It is, how many of you remember, which is the representative of the inventory, in which the boat goes, that means that we all sail smoothly. But when the inventory is reduced, that is the water level is reduced, there are rocks which are exposed below, which will actually, so there is two options: either you can increase the level of water or break the rocks. Do you want to break the rocks, or you will rise the water level? Rise the water level means increase the inventory, that you can sail smoothly. So the logical answer is yes, we'll have to break the rocks. And rocks might be your machine related issues, your people related issues. What are the issues? So in this context, I'll try to put this here. I'll go to sheet 2. Let me open up this grid lines. Let me switch off these grid lines. And I want to explain through what causes instability, okay? What causes instability? Debottlenecking of obstacles. There is the method, and there are 3 inputs to this. Let me draw with a small line here. So this is the method, and method has got 3 inputs. Method has got 3 inputs, and these are also 3 M's. What are the 3 M's? Man, machine, and material. Now tell me something. You got a method of doing something. Before focusing on the method, you have to ensure that man, which means that he must be skilled. You have to ensure that machine must be pakka, and you have to make sure the material which is feeding to it, which is the input material, is excellent. So which should you focus on first? Should you focus on the method, or should you focus on these three things first? On the inputs. So the point that I'm trying to say is, in many companies, they will start from the method, which generally is not recommended. The best thing is to start saying, and that is why if you go into the depth of our understanding on the discussion, what is not stabilized? See, first from measurement to improvement. What we said, what is not measured cannot be improved. So there are 4 steps that we talk about. What is not measured cannot be stabilized. What is not stabilized cannot be standardized. What is not standardized cannot be sustained. And what is not sustained cannot be improved. So what I'm trying to communicate from here through this is, from measurement, you have to, from measurement, heavy rains here. From measurement, you have to stabilize, then you will have to standardize, then you will have to sustain, then you will have to improve. So here, unless we do improvements in these 3 fronts, whatever ultimate method you have is of no use. It's very important that these 3 M's are first controlled before we touch the method. So coming back here to this sheet, you need to find out the causes of this variation, which is first related to man. We should remove the causes of variation related to material, bring it to basic stability, then change your method. Otherwise,